So welcome everybody to Deep Learning Adventures. Myself and Robert and George are the co-hosts of this organization. We've been going for about 1.5 years now. I put a link to our Slack channel, which is pretty active, in the chat, and I'm going to share out the page for our meetup real quick. Let me find it. Here it is. All right, so we study deep learning and machine learning techniques, as well as other topics in AI. We usually mix our sessions between more theoretical, going through either courses or books, and mix in with that some hands-on pragmatic projects or techniques, as well as often having invitations. On our meetup page, we have links to all of our meetups, as well as GitHub that has some of the coding we've done. And if you're maybe joining us from YouTube, you already know about it, but we have a YouTube channel for each one of the courses we've been through. So we'll leave that. If you have any questions, reach out to us. Tonight, we've got another project that kind of goes along with the one that George and Robert and I just finished on, which we went over last session. You can go back and watch that, where we developed a device for identifying particular faces, labeling them, detecting them in photos, and we deployed that out to our phone, to an app on a phone, and demonstrated that. There's another group that Robert's going to talk about that's been doing some even cooler things, I think, with these type of models. So Robert, I'll let you take it away.
Sure, David. Thank you for the introduction. A number of us who have been involved with this meetup have been meeting regularly through another meetup called Bethesda Artificial Intelligence Meetup, Bethesda being a suburb of DC, right outside in Maryland. Although for this group, we have been meeting remotely 100%. A spin-off of that group has been the Visual Edge computing group, which really was motivated, I would say, by Steve Milligan. His efforts about 9 months ago to get a group together that were interested in exploring the power of edge devices and how we could bring the machine learning lessons that we've been learning through these TensorFlow courses, how can we bring them to devices such as IoT and edge devices where so much of this technology is being deployed these days. Out of that group, we ended up at first we were looking for some project ideas, and eventually we found this competition, which was advertised through hackster.com, and I will throw the link up when I'm done speaking here to that. But it's a visual competition, and the idea was to develop a low power, low size, low weight application that could solve an interesting problem at the edge meaning these small devices, electronic devices, phones, be they microcontrollers or other small sensors, anything with less power than your typical laptop. And the idea was to come up with a interesting and new application for this set of devices, and to specifically a visual application. There had to be a camera or visual imaging sensor involved in some way. And many groups came up with some really fascinating projects. I don't know if any of my collaborators on this were going to walk through that, but we can go through that a little bit later in the meetup. Some of the other projects that were done through this. The competition ended recently, and they announced the winners. Our team did not win, but we did see that there were some really fascinating projects being completed out there. I think the winning team was doing something about fire detection using drones. So some really interesting stuff. So before I say any more, why don't I introduce my colleagues and collaborators in this who have done the vast majority of the work on this project. That would be Steve Milligan and Neil Tender. Both are on the call and both will be speaking about many aspects of this project. Seeing as how I don't recall what the first item on the agenda was, but I'm pretty sure it wasn't my section, I should maybe cede the floor to somebody who knows.
Hi, Robert. Yeah, we can just do like a quick introduction, and then what we were going to do is we do have kind of an outline. It's sort of informal. I think this session tonight's going to be maybe a little different. I think it's going to be a lot of talking and live demos and videos and pictures, and we don't really have a slide presentation to give. We're not doing going through a Jupyter notebook or anything like that. So that hopefully it'll be fun. So the way what we just sort of said we were going to do is Steve's going to give kind of like a quick introduction to the project and what it is, and then we'll just go through various, we'll go through the hardware and the software and the algorithms. There's a live demo that I'll be doing a little bit later, and then we can kind of talk about some of the ideas that we had that came out of the project for maybe future work. And I thought there's actually a short video that maybe we could start off with that I think, like a picture is worth 1,000 words. The video kind of says what it is. Let me do that. I'm going to just kind of explain very briefly what the project is, show the video, then I'm going to turn it over to Steve to give a little more introduction, and then we can get into some of the more details. So if that's okay with you guys. For this competition, we decided, after going through lots and lots of different ideas, and somehow one thing led to another, we ended up deciding to build something for bicycle safety. So the idea is to alert a driver, a cyclist, when a car is coming up behind them, because you can't see what's coming up behind you. So I'm just going to show you the very beginning of a video, and then Steve will tell you more about it. So give me a second here. I'm going to share my screen. This is on YouTube. By the way, this is the...
we see it.
Yeah, this is the competition that that Robert was talking about. This have it up here, the Eyes on Edge Tiny ML Vision Challenge from Hackster. And maybe a little later after we go through our project, maybe we can, if we have a little extra time, we can kind of go through some of the interesting projects that actually entered the competition. We can show who the winners are. But the idea behind the competition was to take hardware like these kind of boards, and these low-powered edge kind of boards, and then build something out of them that does something kind of interesting. So here's our beginning of our video. I mentioned it's a bike safety device. We call it the car approaching rear view bicycle alert camera. So for people who bicycle in groups, you'll know right away what CAR-BAC means. When there's a car behind you and you yell out CAR-BAC, it's just alerting everybody else that there's a car coming. So just a minute to this, and then I'll turn it over. Oh, hold on a second. I don't think you can hear the sound. So let me unshare my screen. Just remembered that. I always forget to share computer sound. There we go. Okay, here we go again.
Our application lets you know if a car is approaching from behind, but doesn't generate a notification if a car is passing in the opposite direction, if a pedestrian is behind you, or any other non-threatening circumstance.
Okay. Oh, this is what it looks like. But we'll get into this a little bit more later. All right, I've done enough talking. Steve, introduce yourself.
Hi, am I off mute?
Yes, we hear you.
Oh, okay. Um, Thanks for the great introduction. I think Robert did an awesome job, so I'm not really going to say much more other than to acknowledge some of the other participants. When we kicked this off out of Bethesda AI, we had some other team members. We had Amy Dexter, who's a college professor and project manager. George brought the Flower app to us. Mark Pickett, one of the organizers of that meetup, a lot of AI information. A fellow named Stephen Foscarinas, who's also AI, ML project manager, and a fellow named Eric McCann, who I think also attends this meetup, and Nari Kanan, who's with AWS and AI enthusiast. The reason I mentioned the broader team, over time, our team fluctuated and shrank down a bit because of jobs, medical emergencies, and other things. But we set two goals when we began. One was to learn, and the other was to produce something useful. And I think what you're going to see the rest of tonight is that both of those goals were achieved extremely well. And even people who didn't go all the way to the finish made significant contributions to the project, just in the learning department. I was trying to make up a slide that just had a list of everything that I had learned as a result of this project. And I had to stop because it was just filling up a slide, by itself. So I'm going to stop my comments, but what I would say is that by undertaking these types of challenges, the biggest thing that I've learned is that the learning goes in all kinds of different directions, and you come away from it a lot stronger. And now I'd like to turn it back to Neil and Robert, who did all of the technical work and some of the legwork too, with Neil riding the bicycle. So back to you, Neil.
Okay, great. Thank you. Thank you, Steve. That was a really good introduction. And thanks for acknowledging everybody else who was involved in the project. Yeah, I mean, this happened through kind of the inspiration of all the people he just mentioned. And Steve is really kind of the father of this group. I remember in one of the early Bethesda AI meetups, he stood up and asked, would anybody be interested in doing a little hacking and tinkering? And a lot of people were interested, and this was before the pandemic. And he actually, at one point, we all met, big group of people met in the Bethesda Regional Services Center. And Steve has this pretty impressive box of that he brought with him that's just filled with every edge device you can possibly imagine. He's got the the Google TPU, he's got the Intel Neural Stick, he's got the various Raspberry Pis and Arduinos, and I can go on and on. So I think that was kind of you could tell he was serious, and that kind of led to this eventually. So and then the idea to go into the Hackster competition, that didn't happen right away. It started off with the Flower app, that Flower classifier that Steve was talking about, and then I don't know whose idea it was to do the Hackster competition, because I kind of was briefly involved in the group, and then I kind of disappeared for a while, for several weeks, and then I came back, and that's when someone suggested this, and that kind of gave it another little ignition of energy. And then, but by that point, it was the team had kind of dwindled a little bit. But one thing,
Neil, real quick, before you guys get into the technical solution, given that it was the COVID environment, just for others, how did you guys coordinate the work between you all? Was it emails? Was it, how did you guys?
well, no, I mean, the usual ways. I mean, we had regular meetings on Zoom, and there was a Slack channel, and there were some emails, and yeah, it was at one point, Amy Dexter, the person that Steve mentioned, she actually kind of served as like a project manager for us. So she helped keep us really organized,
Okay.
and make us write things down and stuff. But yeah, it was all virtual. I never saw anybody. The first time I saw anybody was last weekend. I got together with Steve in person to take some videos live. But actually, we were distributed too. Steve was in San Diego like for months, and
Right.
he hadn't been here back in DC until recently. So
Yeah,
I think Amy's contribution really of keeping us together and having that regular meeting once a week where we would discuss progress and exchange ideas, that was really key to the success of this endeavor.
yeah, she was really fantastic. And David, you raise a good point, because this goes back to what I was saying about you learn so much, you have to pause to realize. So just, back to acknowledgements, because we were distributed all over the place. One of the things that we learned was how to use tunnels to remotely access the hardware. That was Eric McCann brought us to ngrok. I know Neil now is, we're going to see some of his expertise in remote logins and SSH. And I certainly learned a lot there. So, your question about how to collaborate and how to connect over distance is also a good example of, if you just looked at the project, you might say, neat. But it also generates a lot of learning around, coincidental to that. And Robert, I believe you were the one, to Neil's point, who got us focused on the bicycle safety in the CAR-BAC. So take credit.
Yeah.
It was interesting to note that enthusiasm for bicycles was a common element of everyone in the group. So I thought that was likely to be a project area where we would self-motivate.
Yes, and I think you made a convincing argument when it got down to, I believe that the other Steve and I were talking about a enhanced child safety, device. And yes, I think
So that could have been a good project too.
Well, we'll talk about that with the futures.
One thing that I really made an impression on me was just like, and we'll get into this more later, but how easy it actually ended up being to pick up pieces and put them together and make something useful. And you realize pretty quickly that the possibilities are kind of endless. I mean, with the kinds of sensors that are out there, the kinds of edge devices and processors and libraries, and it's really easy to just make something. So I mean, I just think of things all the time. So that I'd love to do. So and on that note, this group is going to continue on after this. The Hackster competition was just kind of like a artificial, almost sort of like goalposts that we set that was to kind of motivate us to like move along, and it did. It really helped us get it done to this point that we can have this talk today. We might not have. We might have tried to. There were times when we tried to be a little too ambitious, and it forced us to kind of back off and make sure we finished. So, but all the ideas are still there. So we have a nice framework. And so, this is a little bit of an early advertisement. If anyone in this group is interested in doing some of this work, Steve has his group, and be more than happy to, more the merrier. So on that note, should I get started, and should I start talking tech stuff a little more, or okay? So so hopefully you got an idea from the video that I showed what this is all about, right? So it's, we have this basically built a device that has a camera, and the camera is constantly your eyes behind you when you're bicycling, and it's looking for safety hazards. In particular, the one that we're most afraid of is cars, and cars that are approaching. So I am going to share my screen again, and let's see, get the right one here. So we wrote a report, and I'm gonna, from time to time, sort of scroll through this because for the lack of having any kind of slides, this is what we had to submit for the competition. This was our cute little logo, CAR-BAC, raising an alert when there's a car approaching from behind. And this was entering the TinyML Vision Challenge project. I'm just going to use this for some of the content that's in here. So we already talked about the project. I already showed you this video. We do have a GitHub page, by the way, with all of our source code in detail. So if you're interested, we should probably put that in the chat. Maybe Robert, can you do that? Hopefully he heard me. We'll make sure it's in the chat. And so I'm mostly using this for like the pictures here. So hopefully you guys can see these photos here. Yeah.
Yep.
I'm going to say, okay. Yeah. So this is like kind of what this device as it's currently designed looks like on the bicycle, right? So let me see if I can zoom in a little bit here. I went the wrong way. So what we have is a mount. So we mount onto the rear of the saddle. This is sort of meant for a GoPro, but we kind of repurposed it for this. So we have this camera. It's an Arducam. This is kind of a fancy version of the camera. It's got a lens that you can adjust the focus, and so it's just sitting there and it's on all the time. And then we have inside the saddle bag, we have all of the other components. And then when it's all zipped up, it looks like this. And on the bicycle, it looks like this. So it's pretty compact. And this is not like a, final product kind of thing. You wouldn't want to fill up your whole saddle bag normally with something like this. But for our little project, this was perfect. And let's see. So what are the components of this thing look like? I'm going to go through that next. This is what's stuffed into the saddle bag right here. So what you got is this is the camera that I just showed you in the middle. And then the controller for this whole thing is this, it's a Raspberry Pi. This is what it looks like opened up. You can see it's just a standard Raspberry Pi 4 you can buy off the shelf. And it's inside this case that has a fan to keep it cool. And it's powered by this battery pack over here, which is like one of these off the shelf kind of, bricks that you can get for charging your cell phone when you're traveling. It worked really well for this purpose. And then the last piece, which is, a very important piece, is what you got here. This is the Google Coral, which is their TPU accelerator, which allows us to do the machine vision. There's actually an object detection machine learning model. That's why we got into the deep learning group here, deep learning adventures. And this is what's actually doing the object detection, and which we'll go into, like, that's how it sees that there's a car and detects that we can detect that it's approaching. So all this stuff just gets stuffed into the saddle bag. And then the last piece is this little buzzer here that's sticking out. This is just a simple little piezo buzzer that makes a shrilling sound when it's alerting you. You heard it in the video.
Is that a
Yep.
4 gig or 8 gig Pi, or how much?
Well, how much memory does it
Yeah,
have?
yeah.
It's not the smallest one. I think it's an 8, or maybe
It's a 4.
It's a 4. Hang on. I have the bill of materials here. I just don't remember. It doesn't say here. Okay, I think you're right, Steve. It is probably a 4. We didn't really need that much memory for this application. I I probably bought one that was a little more than we needed because just wanted to make sure we could build something that would work. But yeah, it's you can buy it in a couple different configurations. So let's see, going through the other components. So we talked about the Raspberry Pi, the camera, the Google Coral TPU, the battery pack, the buzzer. Here's some more pictures. This is the Pi again in its case. This is the TPU by itself. This is the battery. This is a kind of a zoom in of how these things are connected to this header inside the Raspberry Pi is called a Gpio header, and this is for connecting, you know, miscellaneous kinds of devices. So the buzzer just plugs right into a couple of the pins here. It can be directly controlled, and then the fan plugs in there to get power. And then we have a detailed bill of materials here. One of the things I found on the internet was this bicycle saddle rail. That's how this thing is attached to the saddle. It's meant for a GoPro, but it worked pretty nicely. Had to buy some kind of GoPro grab bag parts, kind of tinker toy it together. And then again, these are all the parts that I just talked about before. Of course, for the Raspberry Pi, you got to have the SD card. You've got a cable for the camera. You've got some USB cables. You've got some jumper wires and the case. Let's see if there's anything else here. There's some other stuff on the hardware that was kind of interest. They actually cared about this in the competition. It's not just about what parts do you use, but things like power consumption and size and weight and cost. So let me just go into that a little bit right now. So we actually, when this thing was running, we measured the power consumption to see, you know, what it was consuming, and this was also useful for sizing the battery because we wanted to make sure that the battery was big enough that you could run this thing for long enough that the battery didn't die when you're out on your bike ride. So we just took this thing and plugged it in. I happen to have a kilowatt power meter, so just plugged it into there and took measurements. And one measurement is taken with just when it's booted up and idle, and another is when you're actually running the application. And you could see it was like, of course, it uses more power when it's running. It was 5.6 watts when it was running. It was 3.6 watts when it wasn't running. And then you could calculate at 5 volts how many amps this thing needs. And based on the size of the battery, I calculated that, you know, this battery has, I'm an electrical engineer, so this was like natural for me to do this stuff. But it basically calculated out to like 4.5 hours of runtime on this thing, on this single battery. So that seemed pretty good. So we went with it. So that was one factor. I don't know if this kind of power consumption falls in the, I mean, there's lots of stuff out there. They're really going for really low power, like on the order of milliwatts or less. So we're not in that zone here. You would probably need to not use a Raspberry Pi for that and not use a Google Coral TPU. But for this project, you know, as a first cut, this was pretty good power consumption profile. Although I will say, after running this thing for a while, it did get pretty hot inside that saddlebag. There's really not good cooling inside that thing. So it's not really a good thermal design, but one could improve on that. And then the cost, we weren't thinking about cost when we built it, but at the end of the day, we added it all up, and I think we figured out it was about $218 for all the parts put together. So, you know, it wasn't too bad. I mean, I think you could definitely get the cost down if you tried to use, you know, this was like the goal was to build something that worked and not undersize things, and then later you could try to streamline it. Maybe you don't need a Raspberry Pi 4. Maybe you can use like the Raspberry Pi 0, which is their really low end one. I don't know, that might not have enough processing power, but there's all kinds of other stuff out there today you can buy. So something a little more lightweight might work. But we started with this, and this was our bill of material cost. And then size and weight, I guess this isn't really that interesting, but it was a little under a pound, and you know, you can kind of get an idea of the size from the pictures that I showed you. Oh, I also have, let me stop sharing my screen. I have all the stuff right here because I'm going to do a live demo a little bit later, but I'm just going to hold it up to the camera. So yeah, here's the Raspberry Pi. Here's the camera. And here's the TPU. It's all connected together except for the battery right here that I just showed you in the picture. So we're going to use this in a little bit. Just have it sitting on the table here right now. So I think that's everything I was going to say on the hardware. Does anybody have any questions about it? The next topic is going to be Robert is going to take over. He's going to talk a little bit about the software and what you're dying to know, the algorithms that are running on this thing to make it work.
Yeah, Neil, one comment I'd make that about something we learned on the way. The Raspberry Pi 4 that you have there was great for prototyping because it supports all the arithmetic types. We tried an aside experiment to use a Raspberry Pi Zero, and then we learned that the processor was only capable of integer math. So it's one of those things that we could probably get to work in the future, but the path of least resistance went through the 4 that didn't have those limitations.
So that was the question I was going to ask. I think maybe you answered it, but it sounded like all the components you got just work together. Were there any things you tried that failed as far as hardware?
Yeah, and David, I wouldn't even say it failed. What happened? So, again, we were, different team members were sort of trying different things to see if we could get improvements. But as Neil stated, our first goal was just to get something that worked. Interesting thing, when I tried the Pi Zero, I got a 1-line error message and it just said illegal instruction. And it took a couple of days of research to find out that, it runs on an M0 processor that doesn't support floating point. So if you have a properly quantized model, so you've taken all the floating point out, it'll run on that processor. But it's just a question of how much time do you want to spend poking and tweaking in each loop. But yeah, we tried a lot of different things and some worked better than others.
Yeah, Steve, like I said before, Steve has looked into this a lot, and he has a big box full of different devices, and we looked at all of them actually. And these components are all made by different companies too, which is kind of interesting, right? The Raspberry Pi is made by Raspberry Pi, the camera is made by Arduino, and then the TPU is made by Google. And I mean, I'll say it works together. I mean, like, you don't have it's the library. It's all written in Python, and there's libraries for everything, and it just pretty like surprisingly seamless when you buy things from different companies and put it together. And Steve we're going to probably, one of the next steps in this is going to be to try to port this over to one of Steve's other devices, see if we can do it and if there's any benefit. He's got a couple of boards that, like, one has the camera like integrated onto the board directly, and then there's another version of the Google TPU that basically has like the equivalent of the Raspberry Pi and the TPU on the same board. So we think we should be able to do it. So, okay, well, in that case, Robert will talk a little bit about how this thing actually works, the processing itself, because a lot of the processing is happening on the Raspberry Pi. Some of the processing is happening on this Google TPU, and at the end of the day, it's going to turn on this buzzer when there's an alert. So how does that all work? So I'll let Robert, we'll talk about that for a little bit, and then we can get into the demo.
Sure. So I think we misspoke a little bit at the beginning. I do have a few slides to go over the algorithm. I thought that would be the easiest way to see it. So let me share my screen and we can get to it. Can you see my slides here?
Yes.
All right, so just a few slides that I put together to describe the algorithm that we are using for CAR-BAC. And it's a three-step process that is pretty intuitive if you think about it. First of all, you have to detect the objects that you're looking for, and you're detecting them in still frames. Second, you want to aggregate across those still frames to create tracks so that you can get some sense of how vehicles are moving from one track to the next. And third, you need some kind of a classifier to determine, is this track approaching from the rear or is it not? And that's really all there is to it. I'm going to step down through each component in turn. So I think I'll actually, is this large enough for people to read? So I have a number of links that I'm going to be jumping back and forth. It might be easier to not go into full screen mode.
Looks okay, I think. Yeah.
Okay.
Okay.
So we're starting with detection. And we have used the SSDLite mobile det architecture. And this was born out of the original single shot multi-box detector, an algorithm that was published in 2015, developed by Google in conjunction with a couple of different university researchers, I believe. And what was novel about SSD at the time was that it was, well, it's right in the name, single shot. Most detection algorithms, which were, so recall that the objective here is to look at an image, and you not only have to tell that there's something in the image, but you have to identify where in the image it is. So for most of the detectors that pre-existed SSD, you had a two-stage problem where the first stage you actually had two separate neural networks. You had a one neural network that would just nominate the positions where it thought there might be something, and then a second neural network that would actually go through and say, is there something there, and if so, what? SSD streamlined that and made it a single step that can nominate both the positions and the identities of the objects. And it did that through assuming certain anchors and places where objects were likely to be, and then the neural network itself could manipulate that information as it went from layer to layer. So each initial proposal area would eventually maybe correspond to the output location. SSD, as you can imagine, because there's this one neural network rather than two, significantly decreased the computation time, while also slightly decreasing performance compared to the best algorithms that preceded it, such as I think it was faster RCNN, faster region RCNN. The Coral AI model that we're using is called SSDLite mobile det, and that was an alteration to SSD that was introduced by Google in its MobileNet v2. So I guess one of the reasons I stayed here was to be able to click on these links, but we can jump to that one here. MobileNet v2 is, this is the paper that introduced it, inverted residuals and linear bottlenecks, and they described how to alter the SSD architecture to make it even more computationally efficient without losing too much in the way of performance. In particular, one of the things that they introduced there was the idea of replacing some of the convolutional layers. Remember, these are large convolutional networks, very deep, many layers. And some of the regular convolution layers were replaced with depthwise convolutions. So if you can, it may be a little bit difficult to see what's going on in here. There's not a whole lot more detail in the images if you zoom in. But the regular convolutional layer is taking an input image that is a certain height, hi, width, wi, depth, di, and it is mapping it to each pixel in the output gets mapped through the use of a kernel, which is this k-by-k filter that's being slid over the object. And so if you think about the number of computations that have to happen for this layer, each layer, every single pixel in the output, every single pixel, so the number of pixels in the output is hi by wi by dj, is considering all channels in the input, di, and then you have consideration of the kernel, k by k. So the number of computations that occur at this layer in the regular SSD algorithm is given by this formula right here. The innovation of SSDLite was to come up with an approximate way of doing this that's actually separable into two layers that compromises the accuracy and performance a little bit, but is much, much faster because the number of computations is much, much reduced. So what you're doing in the first half of this is you're applying the kernel and you're doing the k by k filtering down to a single pixel. But the difference here is that each pixel in this intermediate output is only being derived from one channel. So every pixel here, if you have a 3 by 3 kernel, instead of having each pixel in your output over here being determined by that 3 by 3 kernel times the number of input channels, here you just have the 3 by 3 kernel being mapped directly to this intermediate layer. So each one of the elements in this intermediate layer is produced by just 9 multiplications. Consequently, this intermediate layer has the same number of channels as the input layer, and so that's what needs to be fixed in this second half. And in the second part, what you're doing is just a depth-wise 1-by-1 convolution. So you're taking all the channels that had corresponded to each position, horizontal and vertically, in the image, and applying that 1-by-1 kernel there. And if you do the math on that in the paper, they come up with this expression here for the amount of computations that you have to do in the second one. And they show empirically that the results for the model are not too much reduced for the cases they're looking at. So clearly, with reduced computation, reduced memory, and reasonably close performance, this is a great candidate for minification to go into smaller and smaller devices. So once we have that model, now Coral does one more step for us. They apply what is called quantization-aware training. And this is something that we covered in a couple of the units in our data and deployment course that we worked through over the summer. You can find some of the videos back on the Deep Learning Adventures YouTube channel. This is from course 2 of data and deployment, where we're talking about edge devices. But quantization-aware training is described in pretty good detail here at TensorFlow's documentation. And the idea is that even though you're doing the training in floating point, you are optimizing it with the assumption that it will eventually be quantized. So you're optimizing it assuming that it will end up in 8-bit arithmetic. And for anybody who's not been exposed to quantization, the purpose of that is to get these computations from floating points, which tend to be represented by a somewhat complicated, relatively complicated data structure, right? With the You have an exponent, you have the mantis at the base of the number, and a sign. And instead, fixed point computations can be done much more efficiently. The trade-off is that you cannot represent anywhere near as many orders of magnitude, hence the importance of the quantization-aware training. You want to make sure that your training is happening with data that are likely to be in the same range of values so that your map from floating point to fixed point is reasonable. Once we get the results of the detection from MobileDet, we have 3 quantities that it outputs: the ID, the score, and a bounding box. The ID is really just a number from 1 to 80, or it would be 1 to 80, except there were some new classes added. This is COCO dataset that we're talking about that these SSDLite model was trained on. And the ID is going to tell us what TensorFlow thinks the object is. From it can only choose one of those 80 classes. And the score is going to tell us how confident it is in the detection. That's a float that ranges from 0 to 1. And the bounding box is going to be a four coordinates that tell us where the edges of that box are within our image. So one more step that we do from the output of the detector is to, first of all, down select by ID. Most of the objects in the COCO dataset were not traffic related, so we chose the ones that were. There's car, truck, motorcycle, and bus in the dataset. We could have chosen bicycle, and I believe Neil did for a few runs when he was testing it, but the current prototype that we're using right now does not have that enabled. You could also consider pedestrians as well, but when you're talking only about threats that you might be exposed to from the rear while cycling, the pedestrian is not really an interesting target. Any questions on detection before we move on to tracking?
Yeah, kind of. Sorry, like just really quickly. So the ID is what kind of vehicle it is?
The ID is what COCO thinks the class is. So it can't tell us what kind of vehicle it is. The best it can do is car.
Okay, but like when you were saying like car, truck, bike, whatnot, that is the ID, like
Well,
classification or
mhm.
whatnot. Okay, and so score is like the confidence for that?
Yes,
Okay, awesome. Thank you.
sure.
Yeah, there's like 80 classes, right? So
Oh man.
so it's got all kinds of things in there, like, you know, pencil and I don't know what. There it is. There's a lot of stuff in
This
there
is the
that
data set. I don't remember exactly where they keep the list of classes. Somewhere in here, there's probably a link to a text file that has them.
Yeah, I mean, this is kind of silly, but like in a different country, it'd be funny if there was like tiger was actually really important. I'm sorry.
Oh my
I'll
God.
stop talking now. Okay. Back to you, Robert.
Well, I have been
I've been chased by dogs before.
I have been
See-
chased by dogs while riding,
Yes.
not tigers though. Yeah, that would be.
Yeah. No, dogs are awful. Yeah, I agree. All right, thank you.
I wouldn't say that as a general statement.
Mm.
Dogs are definitely not awful.
Oh no, yeah, no,
But
they're awesome.
Being chased by dogs is sometimes a little bit scary.
Right. I defer to you. Thank you.
Okay, so the tracking algorithm up next. So now we have the detections. We need to be able to aggregate across frames and say what is the path, the trajectory that each detected vehicle is taking. So Neil found a simple online and real-time tracker, and that was published by a group out of Australia, I think. Queensland University and University of Sydney. And a very simple approach, but surprisingly quite effective. They don't really have too much in the way of imagery here, just some performance evaluation and other stuff in the paper. But they also had an implementation through GitHub that we have borrowed from extensively in order to adapt the tracker to this purpose. So what this simple tracker does is it takes the existing detections, and once you have enough of them, and that enough of them is determined by a hyperparameter down here, min hits. You have to have at least 3 hits on an object to be determined a track. And once you have a track, you start trying to build a picture of where you think that vehicle is moving next. And the sort tracker uses a Kalman filter to do that. And it's a first order motion estimator. So all it's doing is doing the first order linear computation based on previous observations, assuming that each one is evenly spaced in time. Where do we think that the vehicle will be in the next frame? Incidentally, while I was looking this up, I found a pretty cool article here on Kalman filtering, which had some how a Kalman filter works in pictures, and this goes into quite a bit of math with some cartoons here at the top. But I thought it was very well explained and really worth a look. I could drop that in the chat now while I'm thinking about it. So back to CAR-BAC. Once we have a prediction of where each track is going to go, we have X number of vehicles and we're tracking them. Once we have the prediction, the next thing we want to do is figure out, well, suppose we have more than one detected vehicle in our image. How do we want to match them from one frame to the next? We're going to have a variety. We may have multiple predictions for where they're going to be. We may have multiple new detections. So what the algorithm does is it just produces a matrix and does the Cartesian product really of the IOUs, just every possible match of an existing track, all the predictions of that track, and the new detections. And we're looking at the bounding box that was predicted versus the bounding box of the new detection using a metric called IOU, which is intersection over union. This is a very common metric used in object detection, segmentation, any type of problems where you're looking at boxes or overlaps or some kind of thing where a detection is moving around your field of view. The idea here is exactly what it says, intersection in the numerator, the area of the overlap, the blue area here, divided by the total area, the area of the union of the two boxes. And you'll get some fraction between 0 and 1 when you compute this. And the cost matrix is going to be thresholded. I believe it says IOU threshold here equals 4, and that is wrong. It is 0.4. It is 0.4 is the IOU threshold that the sort tracker that CAR-BAC is using. So in order to qualify as a possible match to continue a track, you have to have an IOU of at least 0.4. At that point, you still may have ambiguities. So we run what is called the Hungarian algorithm, matching algorithm. It's really just solving the classic CS problem, the assignment problem. You can read a little bit more about it here, but it's an algorithm that's been around for 65 years, looks like. There's a few hyperparameters involved in the tracking, the min hits that we already talked about, the IOU threshold, and the max age. And max age, what it's doing is allowing the tracks to persist even when a detection isn't happening. You may have one or two frames of bad imagery, and if one frame is missing a detection, you don't want to necessarily drop the track immediately. So there's a max age of 3 that allows the tracks to persist in memory for at least 3 more frames before being discarded. Finally, step 3 is the simplest and shortest step. We're really just asking, now that we have tracks, does this track represent an approaching vehicle? So if you consider the field of view that we're looking at, we have a certain number of pixels, horizontal and vertical, and the track will be considered approaching if those pixels are increasing, if the box height, the box width is increasing over time in the immediate past, or if it is decreasing, we want to say it's not approaching. So there's a couple different hyperparameters that you could look at here. We have an approach tracking depth of 25, and I think Neil chose this just to, based on the data that looked like enough, 25 frames, so it's about 1 second worth of data. I think it's 30 frames per second, so 1.8 seconds worth of data. You're looking at the position of the vehicle, and you're saying, is the angular substance of that vehicle getting larger as the frames are increasing? We also wanted to set an approach tracking threshold, and here we're using the unit 4 pixels squared per frame due to some rescaling that was happening inside. That is something that in the future we're considering looking at again. There may be other ways to rescale. There may be other ways to tune the threshold or regularize it. The basic idea, though, is that we want to definitely reject vehicles that are going away, but we also want to reject those that are not moving relative to us. We really want to only take ones that we're pretty confident are approaching. And so empirically, just from a very quick test, the value of 4 was chosen there. And just a couple of images over here that we'll see more of as we step down through the results. Any questions about the algorithm section overall?
So I think you answered my question, but I was wondering if there was any impact when you are actually going around a curve versus a straight road. But I think if I heard right, it's 30 frames per second is probably so fast it doesn't really matter, right?
Yeah, the frame rate would not be an issue there. I think more the issue might be if the vehicle dips or goes out of the field of view, which might happen as the road goes up and down.
Okay.
I think Neil could probably speak to that a little better.
There are definitely some kind of edge cases that, like, I mean, the simple case is what, like, the car's behind you and the box is getting bigger. And when it's getting bigger, it usually means it's getting bigger horizontally and vertically together at the same time, right? Or it's getting smaller because maybe it's a vehicle is not, maybe it's a parked vehicle or something, so it's not moving. But yeah, when you're going around a bend or making a turn, then it may go from being in the middle of the frame to, like, it may go, let's say it goes to the left and then it goes out of the frame gradually. So that's kind of a corner case. Or so there's a couple of things that we sort of heuristically did in the code that try to handle those cases. We could probably do some more work to make it more robust. This was, again, just sort of a basic make it work activity and it works pretty well. But what you really want to do is road test this thing, and then you'll find all kinds of probably scenarios where it doesn't do as well as you would like, and then you probably can refine the algorithm. So yeah, there's certainly going to be corner cases of things that don't look like what the ideal scenario that Robert is showing here.
Yeah, one of those edge cases that Neil did build in a little check for that I didn't describe was allowing for the vehicle to go partially off the side. And so what just naively considering the box heights and widths might get you is if you're going around one of these curves and the vehicle goes off the screen a little bit, all of a sudden the width might decrease while the height stays roughly the same. So there was a bit of a complicated if statement somewhere in the code that was just checking. It was like, if the height's still increasing, then don't reject it on account of width alone.
great.
Cool. Well, I have gotten to the end of the algorithm part, and I'll turn it over to Neil, I think has the next part.
Yeah, so this
Uh,
is, oh, go ahead, Steve.
Yeah, just before you get off of that, could one of you just, you know, talk a little bit about, you know, why'd you select this software stack out of everything that was out there?
Do you want to take that, Neil?
I'll try. I don't know how to answer that. I guess, you know, just kicked around ideas. I think I think we've all seen object detection many times. Anyone who's been doing this deep learning stuff with images, you know, we've had deep learning adventures courses that we took that went over, maybe not this SSD, but there was one on object detection, I remember. So we've seen what object detection can do. So you can easily imagine that you could pick out a car in a picture. And then the idea that you could track the object is not such a crazy idea either. So the idea, you know, it's kind of an intuitive three-step process, as Robert said. You know, it's like how would you know if a car is approaching? Well, you gotta detect the car, you gotta you know, track it, and then you want to kind of determine, is the track a track that you care about or not. So I don't know. I guess I can't say that there was a lot of different other approaches that were being considered. I mean, it came down to really, okay, how are we going to do object detection? How are we going to do object tracking? And then how are we going to figure out if the track is one that we care about? So, and we'll talk about this a little bit in sort of our lessons learned, but the first two steps, the object detection ended up being kind of right out of the box. You know, this model, this MobileNet SSD, they trained on the COCO data set is something that Google gives you, like, as it's one of their examples that you can get for this from this Google Coral. So we started this, I guess I'll just jump ahead. We started this project thinking we were going to have to collect a lot of data, find some good data sets, pick a model, train the model. We were planning to do all kinds of transfer learning, maybe, to try to come up with a model that really worked well for our data. And at the end of the day, we like kind of started to run out of time, and then let's just try the example from Google, and we tried it, and it like works surprisingly well. It's not really meant for what we're using it for, right? It's got 80 different classes in it, and only like 3 of them are ones we care about: car, truck, and motorcycle. You know, there's all like 77 other classes of things that have nothing to do with bicycle safety, but they're in there. So we could probably certainly have a better model. But, you know, I think we ended up with the object detection just because it was an example, and then the tracker. I think I just Googled like object tracking algorithm, and I stumbled on the sort, and there was a library for it, and it tried it, and it just kind of worked pretty well. And then the last step, the classifier, that was sort of invented it, because it was kind of intuitive, right? The box is getting bigger or the box is getting smaller. It's not all that sophisticated. There's probably much more sophisticated ways to do it, but just to get something working, it was pretty straightforward. Does that answer your question? Is that helpful?
Very much so. Thank you.
Yeah, and just to illustrate that further, I moved the page over to the site where we got the detection model, right? You can just go to Coral provides a number of models that have been pre-trained, and this is the trained models just for object detection, but you actually have lots of models for lots of different other tasks as well. Image classification, semantic segmentation, speech recognition. I think there's some NLP models and other stuff too. I'm not sure all what the offerings are, but at least as far as object detection, you have all these different ones to choose from. And the one that we took is right here, this SSDLite mobile det. So there's 90 objects, but I think that's actually wrong, because 10 of them don't exist in the data set. They're just numbered from 1 to 90, but 10 of them aren't there. But yeah, the Edge TPU model is a .tf-lite file right here. The labels file, oh, okay, we could actually just open that up and take a look at the.
Oh, you found it.
Yeah,
There it is.
so here are all the 80 different classes, and I think if you watch this list here, you'll get 91 strings, but about 11 of them here are an NA. So that's where
Yeah, so
80 classes. So we have a car, motorcycle, bus, and truck are up here in the top.
yeah, so we're not looking for a frisbee or a handbag in this thing, but it is. If there is one in the picture, it'll find it. We just ignore it.
So maybe to Alana's point, we should add dog, bear.
Bear's already in there.
Tiger.
No, I mean not filter
Tiger.
those out, right? The bicyclist.
Yeah, or
the
like
next
person with a knife.
version of CAR-BAC, the bicyclist wants to be alerted that there's a bear chasing him.
That could be
I'll
a new feature.
Yeah, and given the current situation in Maryland, we need to add zebra.
Yes. And most of these are inanimate objects.
I don't think I've ever been chased by a hairdryer before. Well, what I was thinking about doing next here is showing the rest of that video clip, because now that you've given the algorithm, the rest of the video it's kind of a little bit of duplication of what you said, but it's pretty short, and it's got a video to go along with it. So let me go back to that. Where is it? Chromium. Okay.
Should share that sound.
Yep. All right. Here we go. So we left off here. I'm just going to continue the video.
And now I will take just a minute to go deeper into the tech and explain how this device works its magic. The cars are detected using an algorithm called SSDLite, which utilizes a deep neural network called a single-shot detector that is run on the Google Coral using TensorFlow Lite. SSDLite generates bounding boxes around all detected objects, which you see as green or red outlines in the video. There are a total of 80 different object labels in the COCO dataset that the model was trained on, but we are only concerned with a few, such as cars, trucks, and motorcycles. So we simply ignore any objects detected that do not fall in these classes.
I'm going to pause it for a second here. So you see all these cars are being detected, and they all have a tracking number next to it. That's the number of the object detection. And you'll also see my friend is here bicycling behind me, and it's ignoring, it actually does detect the bicycle, but it ignores it. So you won't see a box around him. He's not a safety threat. At least I don't think he is.
And then once detected, the objects need to be tracked. And that is accomplished using another algorithm called SORT, or Simple Online and Real-Time Tracking. The numbers you see next to each bounding box in the video represents the tracking ID number. Finally, to determine if the car is approaching, we monitor the size of the tracked bounding box over several consecutive frames and use a simple linear regression to determine the size if it's increasing. If it's increasing fast enough and over enough frames, then we assume that the car is approaching and we raise the alert and turn on the buzzer. This whole thing was surprisingly simple to pull together. The software is a Python script, and the components are all off the shelf. The model and some example code from Google Coral AI, Python libraries, OpenCV, NumPy, PyCoral, FilterPy. There was only a very small amount of custom code required to combine the pieces and control the system. We were amazed at how fast we could build something that really works and is incredibly useful.
We hope you enjoyed our presentation. For more information, please visit our GitHub site shown below. Have a great day and ride safe.
All right, so that's that. So so what I'll do now is I'll just go into the live demo. If everybody's ready for that. Hopefully we can get this to work. So first thing I'm going to do is I'm going to take this this battery and I'm going to plug it in. And I'm going to let this Raspberry Pi is going to boot up. It's just going to take a minute. And what I've done, I can't actually like ride my bike here right now for you guys because I'm in my office. So what I've done instead to try to simulate the experience is I have some nice photographs here of some cars. Got this nice Kia right here. We have a big truck and sports car here. So we're going to try to use these just to show something live. It's not exactly, it's a little bit of a made up scenario, but so one thing that's really cool is you'll notice that everything that I'm holding in my hand is it's completely wireless, right? I'm not connected to anything. But the Raspberry Pi has Wi-Fi built into it. So I can, let me share my screen. And I'm going to you got my whole screen now. So I can actually use a remote desktop application called Ramina. And I have the Raspberry Pi 4 right here. So I can just remote log in into the Raspberry Pi. So now, even though it's wireless, you are actually looking at my Raspberry Pi desktop right now. Pretty cool, huh? So what I'm going to do is I am going to navigate into the script that I have. If I can find it here. This is it right here. So the script is called. I'm not gonna walk through the code. That's probably going to be way too much detail. But you can see we have a couple different Python scripts here. The one we're going to run here is called Run Live. Run Live is a Python script that has a big, does everything basically. It's got a big loop and it captures a frame from the camera. It processes it through the algorithm, and then it turns on the buzzer if there's a car approaching from behind. It's basically the application. And then there's some helper things in here. There's the sort tracker is a separate module here. There's some utilities that it calls, but so all I got to do is I've got to open up a terminal here. And
Is the buzzer just turned on for a certain time, or is there something to turn it off?
Right now, the way it's, we can change it, but right now it just whenever you see that red outline in the video, it turns on the buzzer, and when the red outline goes away, it turns off the buzzer.
Okay.
I have a newer version of it, which I'm not going to show right now, where it adds a little bit of hysteresis to it. So if the buzzer turns on, it turns it on, and it makes sure it's like a minimum of 2 seconds, because sometimes you'll get like a little blip where it'll detect the car, and then it won't detect it, and then it will detect it, and so it kind of smooths some of that out a little bit to make a little bit of a better experience. But so what I have here is, open this up here. So what I'm going to do is I'm going to run the script. I have one version without the tracking and one version with the tracking. So I'm just going to copy it into the terminal and then run it. And the way I have this thing set up right now is it's actually going to open up a window. There it is right there. So it's running. You can actually see the output of my camera. Whoops, upside down. There's me. Hopefully you can see all that. Okay, and then you're seeing the, on the left here is the terminal window, and you can see it's running, each one of these lines is one frame that it processed. So it's processing it's doing about 8 frames a second right now. In this, it'll be faster if I turn off this, video window, but I think for the demo, it's helpful to see this. So here's what I'm going to do now. I'm going to take, now you can see that it's using the camera. It's displaying the camera onto the screen. And believe it or not, it's actually running the algorithm. You may not realize it, but it is. And the way y'all realize it is I'm going to take this photograph here of a car, and I'm going to hold it in front of the camera. And you see it's detecting the car. If I hold it steady, really steady, it just puts a green box around it, track number 3. And if I start to move the car closer to the camera, it detects it, it turns red, it turns on the buzzer. If I move it away, it turns green again. Move it closer. So you're seeing it running live in action. All you gotta do is strap it onto the bike and you're all set, right? You can hear the buzzer?
Yes.
Cool. And then I got the truck here. It's got the truck. And then this one has 2 cars in it. It's picking them both up. You can see it's tracking them, right? The track number 7 and 9. So there you have it. I don't know where I came up with the idea to print out a picture, but I think Steve and I were working together. We were trying to make a video to do, he was still in San Diego at the time and we were doing it over Zoom. So I actually had it on the bicycle and figured out that somehow this worked. So that's it. That's the live demo. It's also, I have different scripts. Like one script can just record the video, but not actually process it. And then you can kind of post-process it later. So that was kind of useful for doing some debugging. This thing can be turned off. I'll stop it. So you can see that it's processed. In the time we did this, it processed 1,920 frames. Speed was about 9 frames a second. The camera took a 640 by 480 video, but the model is only a 320 by 320 model. So one of the things the Raspberry Pi has to do is it has to resize the image, and that's part of what's taking so long. Like one thing we can do very easily, just ran out of time, is I think we can just have the library for the Pi camera can just capture just directly get a 320 by 320 frame, and then you wouldn't have to resize it, and that would reduce some of the processing. And by the way, this camera is like a total overkill. This is like I don't know what it is. It's a 10 megapixel camera or something like that. And obviously we're not using anywhere near that here. So, I mean, you couldn't put a 10 megapixel image through a TPU like this and have it keep up. So, but you don't really need it, as you can see.
Do you think it would work in grayscale as well?
I don't see why not. I mean, the model is trained on color.
Yeah, that's true. The SSD, like.
So I don't know if you just gave it grayscale, if that would work, or if you could retrain it or find a model that was trained on grayscale. I would think it should be able to do it. So that's the live demo. And then I have a couple of other fun videos I can show. Before I stop this, does anybody have any questions about the live demo?
There was a question in the in the chat about weather, and the snow or rain. We didn't expect you to demo that.
Yeah, actually, no, that's a good question. And, you know, obviously we didn't really test this to that extent, but I do believe that will be a challenge. In fact, well, I found experimentally, I mean, I took this thing out and rode with it, and I found that it actually does better during the day when it's sunny out. And then like if I go out and I ride and it's starting to get dark out and it gets, you know, the sun starts to go down and you're starting to get into that twilight and the cars start to turn on their headlights, it actually doesn't do as well. And I'm guessing the model that we're using is not really trained well for that. In fact, the video I'm going to show you kind of illustrates that. You'll see in a minute. But although I'm sure, you know, there's all kinds of work being done in the space of autonomous driving, and they're doing all kinds of stuff, I'm sure, over all different kinds of weather conditions and lighting conditions and stuff. So if we really wanted to improve this thing, we would maybe be able to exploit some of the work that others have done in the autonomous driving space, you know, not start from scratch. Here, we just used, again, the COCO data set, which wasn't really meant to detect cars reliably under all different conditions. Okay, what I'm going to do now is I'm going to share my screen again, but with a different. I'm going to shut off this Raspberry Pi, and okay, so last weekend, I actually went out with Steve Milligan here. It's the first time I'd seen him in a while, and we met in Rock Creek Park. And I had my bicycle, and he had his fancy camera, and we captured a couple of videos here. So I want to show you that what it looks like. So bear with me for a second here. Okay, so here's one video that Steve took from his camera standing on the side of the road, and I'm riding my bicycle. Hopefully you can see this. So I'm riding my bike, there's a couple cars behind me. See, it's getting dark out. And there's also a bicycle there. See the bicycle? Okay, so that's the end of the video that he took. Now, what I did while he was doing that, I had the CAR-BAC system turned on and recording video. So now that you've seen that video, hopefully you remember what you just saw. I can show you what it looked like to the camera on the bicycle, the CAR-BAC camera. And hopefully I'll get the right one here. It's in here. Here it is. Okay, you have to ignore the first few seconds of it. Okay, so here I'm riding my bike. There's Steve standing there on the side of the road. You can see it's picking up those cars that are parked on the side of the road, but it's not raising an alert. Okay, now this is the moment where Steve started recording. You can see the cars behind me. These are the cars that you saw from Steve's camera as well. Now they're starting to get closer. There's Steve recording it. See him? See, I turned on a different buzzer sound, but it's basically. Now here's the bicycle that you saw before. The bicycle's coming, it's not raising any alert for the bicycle. It's only raising an alert for the cars. So that was pretty cool. That was the first one. Yeah.
Is the recording actually happening on the Raspberry Pi?
Yes.
So would it be faster as far as the frames per second it can do if it wasn't having to also record at the same time?
Yes.
Okay, just curious.
Definitely. But for this, I wanted to record it for obvious reasons. Here's another one. This is just me writing again. In this case, there's no threatening situation. So you'll just see that it's not going to turn on any buzzer. There's Steve again. There's a car going the other way. I don't know why it started again. Okay. And then we got the third one here. This one actually has cars. let me pause it for a second. So you see, I'm a little disappointed. I would have liked it to pick up this car by now, but there's a couple of problems, right? One is you can see the picture is very blurry. And the reason I think the picture is very blurry on all of these videos that I'm showing you right now is because I didn't have this camera adjusted very well. It's my fault, my bad. This lens has an adjustable focus and I didn't adjust it. So I had it obviously in a bad position. I couldn't go back and redo this. We already had the video. So I think this performance of this is suffering somewhat from the fact that that the pictures are all a little blurry from the focus. And then it's a little darker out at this point. So as I said, if I had done this earlier in the day and I had the camera focused better, I think it would have picked up the car by now. And it still will pick it up. It's just not picking it up early. You want to get the alert. You want to get the alert, you know, as early as possible so you have time to be aware that there's a car coming. But
I think we also talked about the way that the algorithm decision was hurting performance at long distance, right? We wanted to make sure it wasn't giving too many false alarms, but there are adjustments we could make to improve that as well.
yeah, I mean, when the car is further away, it's smaller, the box is smaller, so there's probably some adjustment that should be made, you know, to handle far and near a little differently. Okay, now the last video I'm going to show is a little different. I had to play around a little bit to get this working, but it's pretty cool. So now what I'm going to show you is a split video. So I managed to get on the left side of the screen. Let me just start it. Pause it. Okay, so on the left side of the screen is the video that that Steve recorded standing on the side of the road with his camera. And on the right is the corresponding video that's being recorded by the CAR-BAC system in the bike. And I tried to line them up pretty closely so you can see, you're gonna have to watch this closely as it's running. You'll see both the, you know, kind of both what it looks like from the side of the road and what it looks like from the back of the bike at the same time. Here we go. See the car appears there, and now it appears here. See the car is approaching me from behind. Did you follow that?
Yep.
Cool. So we had fun with that. Well, that is the end of my live demo. I think you get the idea of what we did now and how it works. The next thing is on my list here is that Steve was going to talk a little bit more about kind of next steps, what you know, ideas for improvement and next steps, and any can maybe go into any more stuff on the lessons learned or close it out.
Yeah, I think unfortunately I'm about timed out. I have to go pick up the wife. But I think you guys did a great talk and really illustrated that we learned a lot on this project, and we're looking to learn more. And some of the things that we looked at specifically for the way forward were smaller devices like the Sony Expressence board that has multiple CPUs on it, but is designed for low power. Also looking at FPGAs with the Xilinx Crea evaluation board, and continuing on with our investigations even of like different Raspberry Pi configurations. So anybody who's interested can reach out to any of the people that spoke tonight, and we'll be looking to start our next phase shortly. So thanks.
Very cool.
Yeah, some other areas for further work include doing some cleanup and tuning of the algorithms. We had a few ideas on that. And there was also some thought of building different features ancillary to the main function of it, such as recording video and automatically clipping and sending video if you're attacked aggressively or something.
Yeah, and we talked before about porting it over to other devices. You know, I mean, I'd like to try to get into a smaller form factor. I thought it'd be kind of fun to build a few of these, maybe like 3 or 4 of them, and give them to some cycling friends and stick it on their bikes and let them try it and see what they think. I'm sure you get some really good feedback, right? They'll say, oh, this thing stinks, or this thing, oh, this is great. And they'll probably say, well, if only it could do this, or if only it could do that.
Right.
One of the biggest lessons that we learned, and I think the others have mentioned it as well already, but it was really surprising just how well this worked with such simple components off the shelf. When we first conceived this project, we were trying to think of all kinds of ways that we could address it, and it really seemed like a much more complicated project than it turned out to be. I remember poring over data sets collected from Lift 5, which is the massive publicly available data set that Lyft created through their self-driving vehicles, thinking that we were going to need to take this data and do some transfer learning on it to apply to the case where we're a bicycle in traffic instead of a car. And it was really quite surprising to see how well these models right off the shelf, SSDLite, that hasn't been trained for traffic at all, did on this problem.
Pretty awesome. It's a great example of how much more you learn like hands-on than just like studying, you know. Oh, it's really awesome. Anybody got any questions for the group?
Hi, this is Kumar. First of all, great work, very inspiring. And my question is like, I have like 2 questions or maybe 3. So like, one is, while coding, did you have to like do something differently to keep the power consumption low?
Not really. We didn't really do anything special to try to keep the power consumption low. Basically just built it and measured the power and determined what the power was and determined how big of a battery we needed. And we were able to get a battery big enough to do it. So we stopped there. I mean, there's absolutely positively ways to get the power down on this thing, including coding optimizations. Like I mentioned before, like instead of having to do the scaling of the frame in using the OpenCV library on the Python, if you could just have the camera directly capture the right resolution, that would save some processing and would save some power. Moving to lower power devices. I mean, this Raspberry Pi 4 is probably an overkill for this. It's got more processing power than we need. But yeah, we didn't put a lot of effort into making the power lower, but we could.
Got it. So my next question is like, is it possible to use a mobile phone to do this? Like, can somebody just take their mobile?
Robert, you could take that one.
So you would want to get the model from a different source. We got models from Coral.ai because that were trained specifically for that Edge TPU. However, one of the nice features about TensorFlow and TensorFlow-Lite is that the same basic file formats can be applied in a variety of edge devices. And the Android and iOS operating systems on your phone can run TF-Lite models through the TF-Lite interpreter. So you'll want to train it a little bit differently in TensorFlow, but you can find versions of these detection models that are compatible with those systems as well.
Cool. So my last question, is it possible that the car moves so fast that the device cannot detect it?
It would have to be pretty fast because we're capturing 30 frames a second. Obviously, this live demo I showed was only like 9 frames a second, but yeah, I don't think so. We didn't really test it, obviously, but 30 frames a second is hard to imagine. You know.
Yeah, we didn't want to test it on the freeway, on the Beltway or something.
I don't think you want to be riding there. Interesting question, though, to think about that.
I think it would have to be.
Thank
I think it
you.
would have to be very fast, unreasonably fast. But again, I think one of the things that we would like to improve is to detect at longer range, especially for faster moving vehicles. And I think for a very fast moving vehicle, it might not give you much warning.
Got it. Okay. Thank you.
All right. If there's not any more questions, I'd really like to thank you guys for talking about this. This is an incredible project and really fun way to present it. I like, watching this live demo and the videos is just really exhilarating. So great job. Look forward to hearing about the future developments. And I'm sure this has a lot of other, as you said, what can you do with pedestrians wearing this, or, there's just I'm sure you have like 10 other ideas or more have come out of this. So
there were a lot of ideas discussed in the early meetings for sure. It's been an absolute pleasure working with the team. It's been great to, as Steve said, our objectives were to learn and to build something useful, and I feel like we did both of those things, as well as really built working relationships and friendships while doing it as well.
Nice.
Thanks for giving us the opportunity to present this at the Deep Learning Adventures.
Oh, sure, anytime. And that goes for other people. If they have some interesting projects, please reach out to us. We'd love to hear about it. I'm going to share my screen here at the end really quickly. Show. Always hard to find my window. So I just want to bring up that our next 2 sessions, which are going to be next Wednesday and the following Wednesday, are about transformers and natural language processing. So we'll have a couple of sessions. The first one will go through the kind of the theory behind transformers and attention and how it works. And then the second session will be a direct application to a fun project or a fun competition that actually was run on Kaggle, if you know that platform. So we're looking forward to that, and I hope you can join us for that.
And Dmitry Livonian will be leading both presentations with small contributions from the rest of the team.
That's right. He's pulling the main thing here. So join us for that, and thanks again. And we'll try to have this recording up on YouTube in a day or 2. So if you want to catch up there or watch it again, please do. I will go ahead and we can go ahead and stop the recording now, Robert.
All right. Good night, all. Thanks for joining us.